All right, welcome back. So starting from today, we'll be talking about actual chemical reactions, class by class, or reaction site by reactions class. So basically, just to give you a preview in what we're gonna do for the rest of the quarter, we'll start by talking about reactions with alkene, so molecule with double bonds. And then we'll move on to talk about reactions with triple bond, which is alkyne. And then haloalkanes, so molecule with a bond to a halogen group. And at the end of the quarter, we'll be talking about a series of reactions called nucleophilic substitution or beta elimination. So that's a preview of the rest of the quarter. So remember, in the first half of the quarter, we discussed all the vocabularies of organic chemistry and also like rules to do error pushing, how to identify nucleophilic, electrophilic sites, what are the reactive intermediates. So starting from today, we hopefully will be using all the terms that we learned in applying them into actual chemical reactions. All right, so let's get started on alkanes. So chapter 5 and 6 are all alkanes. First, we'll go over the basic properties of alkane, and then start by talking about what are the general reactions alkanes can undergo, and also discuss them reaction by reaction regarding like mechanism, selectivity, and everything we want to know about these reactions. So let's get started on alkanes. Well, first of all, we want to review the structure of alkene. So alkene, as we know from the functional group side, these are molecules with carbon-carbon double bonds, right? So naturally, we want to discuss how many double bonds are there from looking at the molecular formula. So in this case, we do that by calculating the degree of unsaturation, DOU, or the index of hydrogen deficiency. Sometimes people use both terms, so they are the same thing. So this degree of unsaturation or the index of hydrogen deficiency, it tells you the number of pi bonds or ring structure in an unknown molecule. All right, so in this case, what does it mean? It means the DOU gives you as a hydrogen reference. So what is hydrogen reference? So this one is 2n plus 2, where n is the number of carbon. So 2n plus 2, that's the number of hydrogen if we're looking at a pure alkyl species. Like if you have only these alkyl species, the number of hydrogen always equals to the number, 2 times the number of carbon plus 2. So that's where our reference. So n is the number of carbon in your molecule. And then you minus the number of hydrogen in the molecule. Now, this number of hydrogen in the molecule can actually be a little bit more complicated depending on the number of heteroatoms we have. So in this case, we're referring to the hydrogen of the molecule equals H plus the number of halogen minus the number of nitrogen. All right, so in this case, if you have chlorine, fluorine, or bromine, so you want to add that X into the formula, and you want to minus the number of nitrogen. All right. So knowing the degree of unsaturation can help us by drawing the molecule correctly. And if we have oxygen, just ignore oxygen in the calculation. Oxygen doesn't contribute to these. For example, let's say we have a molecule which is C6N2OH6. We could ask you to calculate the DOU of this molecule and sketch a possible the bond line formula of this molecule, as long as it fits the DOU. There are multiple ways you can do it, but we can always start by calculating what is the DOU. Now in this case, my DOU equals to 1/2 times my reference. So we have 6 carbon plus 2, so that's my H reference, which is 2N plus 2, and minus the number of hydrogen, so we have 6, and we have 2 nitrogens, so we want to do plus, minus 2. All right, wait. Sorry, so this entire thing is in there, so this becomes a plus 2. All right, so this one is my H molecule, which equals to H plus X minus N. You do the calculation, you end up getting 5 total degree of unsaturation. Yes? Yeah, so this is entire thing equals to the H molecule, yeah. All right, so then how do we draw it out? Well, we have a degree of 5, degree of unsaturation of 5 in this molecule. So we can draw it with, well, we need to have some ring and some pi bond. So one of the options to draw it is to have 1, 2, 3, 4, and then a oxygen, an H2. And then we can do a sanity check by counting the number of atoms in here. We have 1, 2, 3, 4, 5, 6. So that's a C6, and 2 oxygen, and we have 1, 2, 3, 4, 5, 6, H6 in this molecule. There are different ways to draw this molecule. Because we have different constitutional isomers, obviously. Like you can move this nitrogen into different position. But I'm just showing like this is one of the way we can ask you a question, right? So we give you a molecular formula, ask you to calculate the degree of unsaturation based on the molecular formula, and then ask you to draw a possible, or 1 or 2 possible constitutional isomer of this molecule. Yes? You mean how I make this one? Well, I make this one because, well, I'm thinking about I need 5 degrees of unsaturation. So you can do it by putting double bonds in there, but you can also do it by adding ring structures in there. So I like to do it this way because I was like, okay, so we have 6 carbon, and let me just make it a arrow ring. It's the same if you want to draw it in this case. You can also draw it as a all carbon arrow group. And oxygen, and then it just have a very unhappy structure at the end. Like there are different ways you can draw it. It's not necessarily the only solution. As long as you keep the number of double bond and the ring structure add up to be 5, it's all correct.
So how does the 5 show through?
Okay, where's the 5? Now we have 1 double bond, 1, 2, 3, 4, 4 double bond, 1 ring. Adds up to be 5. All right, so a ring also counts as a degree of unsaturation. A double bond counts as a degree of unsaturation. So the number of ring plus the number of double bond need to add up. A triple bond is counted as 2 degrees of saturation because we have 2 pi bond in that case. All right, so that's a degree of unsaturation. And also some review in what you already know about the pi bond in the alkene. So if we use ethene as an example, so these are the things you already know, like how to draw the pi bond of your ethene. So in this case, I'm just going to do this with you again, like a review, thinking about what is the bonding in my ethene. Now for my ethene, each of my carbon is, what's the hybridization of my carbon in ethene? That's sp2 hybridized. Or the other way to put it, if we look at the atomic orbitals of my sp2 hybridized carbon, they look like this. So you have sp2, 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 and p. You put the electrons in, 1, 2, 3, 4. You have 4 electrons, 3 in the sp2 making single bond, 1 in the p orbital making pi bond. Right, so if we sketch the bonding of my ethene, it looks like this. So you have your sp2 atomic orbital of your carbon, and likewise you have your sp2 atomic orbital of your carbon. Right, so the sp2 makes a single bond between your carbon-carbon, and also the single bond between your carbon and hydrogen. In addition, we have this leftover p atomic orbitals. And the shape of my p atomic orbitals is perpendicular to the sp2 atomic orbitals. And in this case, we're saying the overlap of the p atomic orbitals gives me my pi bond. And remember our burger example? So your pi bond is actually both on top and below the sigma bond. So both spread are your pi bond. All right. And also in our previous cases, since we know these pi electrons, they can act as nucleophiles. Right, so these are all reviews on what we discussed before regarding the bonding of ethene, or that's the nature of your pi bond in ethene or in alkene in general. What else do we know? We also discussed the stereochemistry of double bonded species. So for a double bond, for example, in this case, depending on the things attached to it, you can have R and R prime group attached to it. So that's called a cis configuration when the two larger groups are on the same side with each other. And we went over that these carbon centers are stereocenters, meaning if I change the connectivity of the group attached to my stereocenter, I'll be forming a different stereoisomer. So in this case, if I manually switch my carbon and R prime, we'll be forming a different stereoisomer, which is my trans isomer. All right. And if you think about it, like why is these two species cannot interconvert with each other? So this one is somebody left their molecular kit conveniently. Thinking about a single bond, right? We have free rotation of the single bond, right? So a single bond, you can have free rotation. Remember, you have Newman projections that you're talking about the rotation, whether you have staggered or eclipse. Some of them is higher in energy, but after all, you have free rotation over the single bond. But if now we're making it a double bond, like this, and lucky enough, they have a very flexible molecular kit. So now I have a double bond, right? So now my double bond is like really stiff. You no longer have free rotation around the carbon atom. And thus, if I want to change the position of these two groups on my carbon atom, I cannot rotate it for it to take place. So that's why whenever you have a double bond, the cis-trans isomerization does not take place under room temperature without like catalyst or anything. It's like stiff enough, you cannot rotate it. All right? These should all be like review of things we already discussed, but just refresh your memory because these will come back and we'll use it when we discuss reactivity or reactions of alkenes. And before we move on, we also have, nomenclatures, right? So just to refresh your memory on the IUPAC nomenclature. the number of the longest chain of carbon atom that contains a double bond in the direction that gives you the double bond, the lowest number. So when you count the chain, you want to count it so that your double bond has the lowest number. Like for example, if we have a molecule like this, right, so I want to count it from 1, 2, 3, 4, 5. And then locate the double bond by the number of its first carbon. So in this case, I'm looking at a pentene, and my double bond is at position number 1. So we can call it 1 pentene. All right. And likewise, we can have a more complicated example. Let's say I'm drawing something like this. So I want to count it so that my double bond has the longest chain. So I start from my double bond, 1, 2, 3, 4, 5. And I have a substitution at this position. So that's at position 2, I have a ethyl group. So the IUPAC name of this molecule is 2-ethyl 1-pentene. Yes?
Do you not go off of the longest chain starting from the top and going?
Well, so in this case, we want to make sure my double bond has the lowest number. So that's like I know what you were saying. You're saying, okay, 1, 2, 3, 4, right? So we want to make sure my double bond is in my main chain. Yes?
The double bond is more important than substituents at this point, right? Like, for example, the double bond was on the 5 carbon there, but the substituent group was on the right. Will we start from the left, or?
In general, we'll start from the double bond with the lower numbering.
Even if that's the substituent group.
It depends on what substitution is it. If it is another double bond, then we have to take consideration of both and make sure they are both like lower, right? So case by case. And we have several common names that contains with like double bond containing functional groups. Like for example, when you have a CH2 group attached to a double bond, double bonded to something else, sometimes we call it methylene or methylidine. And you can have a ethynyl group, or we call it vinyl group. Or when you have a 2-propanol group, we call it allyl group. So in here, the allyl group is probably the more important one because we spend a lot of time talking about allyl hydrogen, right? So in this case, a allyl hydrogen is referring to the hydrogen that's neighboring to the carbon that's double bonded. Or these are my allylic hydrogens. Right. And like what we were saying, we have cis-trans stereoisomer of your alkene, or people also call them with the EZ naming system. So it's a little bit like your RS system for your absolute stereo configuration of a chiral center. For a double bond, we have the EZ naming system. So if the 2 higher priority group are on the same side, we call it Z, or these are my cis higher priority group. And if your higher priority group are on different side with each other, these are my trans higher priority group. All right. We can also infuse the EZ naming into nomenclature of your double bond containing molecules. So for example, if we have a molecule like this, right, so we first look at it, we'll be like, okay, I have my double bond here. I want to contain my double bond in my main chain, and make sure I have my longest chain possible. So let me see, 1, 2, 3, 4, 5. Right, so it is some kind of painting with my double bond in my position number 2. And then I think about, okay, what are the other things we know? I have a methyl group on my position 3. I have a methyl group on my position 4. So we have a 3,4 dimethyl. And in addition, I have this double bond here. Now thinking about this one, the methyl group relative to hydrogen is a higher priority group. And this isopropyl group relative to methyl is a higher priority group. So my 2 higher priority group are cis to each other, or this is a Z 3,4 dimethyl 2 pentane. Yes. So Z tells us the higher priority group are cis to each other, or they are on the same side of the double bond. A trans or a E configuration is telling us the higher priority group are on opposite sides. So if we actually look at the molecule, a cis or a Z group means I have, say, 2 methyl groups that are on the same side with each other. A trans will be the methyl group is here and here, right? So they are on different sides with each other. Well, so in this case, thinking about, we're always, the relative, it's the higher and lower priority is always relative. So we're always focusing on the carbon with 2 things around it, right? So on the left carbon, you either have a CH3 or you have a hydrogen. So comparing the CH3 and the hydrogen, my CH3 is higher priority. Alternatively, if we focus on the right-hand side, now you have a methyl and a isopropyl group. Right, so comparing your methyl and your isopropyl is a higher priority. And then we look at the relative position of my higher priority group around the double bond. And we see, okay, so the methyl group and the isopropyl group are on the same side. And that's how we assign the EZ naming.
Sorry, there's no X or Y.
Where does the X and Y come from?
I just thought Z like total, so like the right hand rule.
Oh, no, yeah. All right, so the EZ naming system is for double bond only. Like these carbon are not chiral centers, so we don't have R or S configuration. We only have E or Z. Let's do it one more time and see if this makes more sense to you. So, one more time. So assuming I have, let's say, something like this, chlorine, methyl, and then something like this. All right, again, for nomenclature, I want to put my double bond on my longest chain. So in this case, 1, 2, 3, 4, 5. I started from the left so that my double bond is at carbon 2. So again, this is a pentane. And it is some kind of 2-pentane. And then I add my substitutions on there. Well, in this case, I only have 1 chloral group on my carbon 2. So I add my 2 chloral. And thinking about what is the EZ stereo configuration around each carbon. Now thinking about the left carbon, we are comparing my chloral with a methyl group. So in between my Cl and CH3, my chloral is a higher priority group, right? And focusing on the right carbon, you have either an ethyl group or a hydrogen. So among the ethyl group and the hydrogen, your ethyl group is a higher priority group. And then you're looking at the relative position. You'll be like, okay, so the Cl and the SL group are on different side of my molecule. So this one is a E isomer. All right. So that's as far as the, like naming for linear alkenes go. And things can get more complicated when you have a ring structure attached to it. Now, for cycloalkenes, meaning a ring containing a double bond. Again, thinking about the cis-trans isomerization, what we're saying is whenever my ring is smaller than 8 carbon, we can always assume the double bond is cis. So you don't have to specify it being a cis double bond. Like for example, if you have a cyclobutene, you can always assume this double bond is a cis double bond. Yes.
Would that automatically make it Z configuration?
Right, but we just don't need, you just don't have to say it. Because for ring structures containing double bonds, unless the ring is like really, really big with 8 or more atoms, we can always assume it is a cis double bond. Now, of course, when we have like larger rings or macrocycles, then we might also introduce the E or Z configuration into the drawing. Yes?
So if we get something like this, we don't need to write E or Z?
No, this one you can just call it cyclobutene. Or in the case, you can also have substitutions on them. Like for example, if we can have this structure, right? So it's a cyclohexene. And on position 1, 2, I have 2 methyl group. So I can call it the 1,2-dimethyl cyclohexene. And I think my note is wrong. I need to update it, by the way. Yeah, then it's like 1 chlorine, 2 methyl cyclohexane. They still have to be cis, right? So the cis comes from the ring structure is asking my ring angle here. You cannot have a trans geometry, otherwise it's a highly distorted geometry. Yes. Right, so let's do it one more time. Let's say we have something like this. I'm just randomly putting an isopropyl group on there. And what do we have? Now we have my 1, 2, 3, 4, 5, 6. So this one will be a 5 isopropyl, 1 methyl cyclohexene. I still want my cyclohexene to be as low as possible. You don't have to do E or Z for these small ring because they are presumably all Z or all cis.
But what if it's in position 4 directly opposite? How could it be cis?
Well, it doesn't matter where you put the substitution. So we're talking about this double bond here. Okay, so around this double bond, again, if you look at this double bond, now around this position, you can have like a methyl group or the ring structure. All right, so in this case, this one is higher priority, yeah. So we're always talking about like this ring, like you can't have a trans bond. All right, so that's about it for the nomenclature. You have the IUPAC nomenclature, and then for the ring structure, these are some of the special cases. And just for additional reading, if you're interested in like names of these cyclohexane or like dienes, your textbook also provided other like common name for different classes of exotic compounds. So these, I'm not gonna test you on it, but we also have concept like bridgehead alkenes, like a norbornene. So basically it's a fused bicyclic ring with a alkene. Or you can have diene. So in this case, you can have the S-trans 1,3-butadiene or the 1,3-cyclopentadiene. I'm not going to test the nomenclature of these molecules for you, but just so you know they exist. More exotic molecules exist. Yes?
Sorry, so going back to the ring, if you had a ring that was greater than 8, would a trans just be one on top, one on bottom?
Right, so for ring structures larger than 8, then the ring strand becomes negligible or very small, and then you can have trans bonds. But those are more special examples. All right, and next up are some of the physical properties of alkenes. So like alkenes, so alkenes themselves are all like carbon hydrogens. So they're generally nonpolar, insoluble in water. They are soluble in like nonpolar solvent, but not soluble in water, right? Like dissolves like. So for alkenes, it's very unpolar, so it's not dissolvable in water. And like alkenes are the only attractive forces available for alkenes are dispersion forces or London dispersion forces. So depending on the size of your alkene, you can have decreased boiling point when you have like smaller alkenes, increased boiling point when you have larger alkenes or larger chains. So if we give you the melting point and the boiling point, you should be pretty straightforward to predict what phase it will be at room temperature, which is like 25 degrees Celsius. Right, so for a simple ethane, it's gonna be a gas. For a butane, well, since my boiling point is only -6 degrees Celsius, that's also a gas. But if we go one more carbon to become a pentane, then it's likely to be a liquid. Physical properties, longer chains, more likely to behave as a liquid. Smaller chain, more likely to behave as gas, because after all, we only have London dispersion interactions or dispersive forces. The bigger the molecule, the stronger or the more dispersive interaction we have. All right. And moving on to one last bit of alkenes in biochemistry. So alkenes in biochemistry is pretty common. We see it in two different forms. One is called the terpene hydrocarbons. So basically in this case, we're saying the carbon skeleton of terpene can be divided into different isoprene units. All right, so a terpene is divided into multiple isoprene units. So some of the example will be, let's say we're just looking at something called myrcene, which is a class of terpene. And its isoprene unit. So when we are looking at the terpene and the isoprene, we are only looking at the carbon skeleton. Like for example, in this case, if we're counting the isoprene, we're saying we have 1, 2, 3, 4, that's your main chain, and on C2, you have an additional carbon. So when this isoprene adds to form a terpene, will be like, let's say my 1 is my head, and my 4 is my tail. Your isoprene would add or dimerize on itself from a head to tail kind of way to say like, okay, so this one is my 1, 2, 3, 4. I have a carbon on my C2. And then this one will be my 4, 3, 2, 1. All right, so when looking at isoprene and terpene, we're not looking at any specific chemical reaction. The position of the double bond is also changing. The number of hydrogen is also changing. We're only looking at the carbon skeleton. So these terminologies are more commonly observed in biochemistry. Like people use the term terpene and isoprene in biochemistry to describe the carbon skeletons. Yes.
What is a terpene?
It's just a terpene is formed by several isoprene units. And that's as far as I can go. And there are several different types of terpene. It's basically like a class of molecule that's important in biochemistry. Yeah.
So would you expect us to be able to like just flip it, or like how would you?
So this one, I don't have a better way to teach it. It's basically just looking at the carbon skeleton and thinking about, okay, so if this carbon skeleton is adding like head to tail to each other, where should I break it? And let's look at an example together and see if it makes more sense to you. Let's do one example and I'll take more questions. Okay.
Isn't the one supposed to be on that double bond?
This one is on the double bond. 1, 2, 3.
Yeah, and then so in your terpene, is the one in the correct spot, or is that?
Oh no, okay, so in terpene, our numbering is, this is independent from the IUPAC numbering. So these are two different things, don't mix them up. So in this case, I'm just showing in the terpene how things are, why this is a terpene, because it is formed from two isoprene units from a head to tail way. They're not identical. So the terpene, looking at the carbon skeleton, the terpene is a double of the isoprene's carbon skeleton, ignoring all the functional group. Let's look at one example together, all right? So let's say I'm giving you a terpene with the following structure. All right, and one of the example question we could ask you is, from this terpene, can you identify its isoprene unit? So that isoprene unit only need to have you only need to find a breakpoint so that the carbon skeleton of the two isoprene units are the same. So when finding the isoprene unit, like we don't have to think about all the double bonds or the functional group. So we can just simply rewrite it based on its carbon skeleton. All right, so this is the carbon skeleton of this linear molecule. Yes.
Why do we do this though? Like,
well, it's just important in biochemistry. As an organic chemist, I really don't care about it, but you'll encounter it in biochemistry, and your biochemistry professor will be very upset if you don't know it. All right? But, yeah, okay. But you need to know how to do it, because, I mean, it's going to be important later on in biochemistry. Okay, don't tell your biochem professor that. Anyway. All right, so how do we do it, right? So first of all, you abstract that terpene molecule into its carbon skeleton, and then thinking about, okay, I just want to find a breakpoint so that I can find two identical isoprene units. So if we count 1, 2, 3, 4, 5, 6, 7, 8, we have a total of 8 like carbons in my skeleton. So I somehow want to break it at position number 4. So I must break it this way. And I'm thinking about which is my head, which is my tail. All right, so this one, I have a carbon on my position 2. So here, I also have a carbon on my position 2. So in my isoprene unit, that's my 1, 2, 3, 4. That's my 1, 2, 3, 4. And these carbon skeleton are the same unit or the same isoprene unit. So I can write my isoprene unit as something like this. Now, in reality, it is a diene like that, but as long as you get the carbon skeleton correct, that's about it. more likely we'll ask you the question by giving you both the isoprene unit and the terpene unit and ask you to do a mix match of the two sets. Yes?
How about the carbon on the bottom right? Like you drew the carbon skeleton, isn't there a carbon on the bottom right?
Yes, that's the carbon on my carbon 2. Right, so that's the substitution on carbon 2.
The one on the left is 1, what about the one on the right is that?
This one is 1, this one is 2, this one is the substitution on my carbon 2. All right, so the main chain, in the main chain, you have 1, 2, 3, 4. That's your main chain. That's the 4 carbon of your main chain. But you also have a side chain on your carbon 2. The same applies to the top unit. You have 1, 2, 3, 4. 1, 2, 3, 4. And then you have a subchain on carbon 2. So that's when we say that, that's what I said when I say the carbon skeleton. All right. One last bit on the double bond in biochemistry, which is double bond in fatty acid. So this one is really nothing fancy. Again, when we're talking about physical properties of these double bond containing species, we're saying, okay, their physical property is affected by the London dispersive forces. So for a fatty acid without double bonds, you'll have all the linear chains, so they can pack with each other pretty densely. All right, so that's why you have a pretty high melting point, because these alkyl chain can pack on top of each other pretty densely. But introducing a double bond or introducing unsaturation into your fatty acids, we're introducing more spacing between your fatty acid molecules. So adding a double bond, meaning you have more separation between the fatty acid molecules, and hence we're expecting these fatty acids with double bond to have lower melting point. So this is, I'm trying to make a link between your actual observation, right? So that's why your, like for example, the stearic acid, so the all saturated acid, they're generally speaking solid on the room temperature, but your oleic acids, these are fatty acid that's liquid on the room temperature. All right, so these are all the fundamentals of alkene containing species. And I have about 7 minutes. I want to quickly introduce to you what are all the reactions we will discuss in our next week's lecture. So, getting started, in our next several lectures, we will discuss various reactions of alkene. In general, in most of these reactions, we're talking about the reaction. You're starting from an alkene, some kind of double bond containing species. Now, this little line just tells you it can be some kind of substitution. Can be a methyl group, or can be a longer chain, or you can make it a diene, but basically you have something attached to the alkene. On the right-hand side, you have a bunch of things, whether it's HCl, H2O, bromine 2 or halogen, and then you can have the mercury, and you have BH3 or ozonosis or H2 hydrogenation. In these cases, we'll discuss general reaction mechanism for most of these reactions, and also selectivity of each of the reaction, and then specific reaction conditions. So at the end of the chapter, you'll have an idea about how do I predict the reaction outcome from knowing the reactant and your condition. Or we give you the product, we give you the condition, can you go back to say, what are the reactant I need if I want to make the product I desire? All right, and we will go over all of them together. And before we do that, well, we again want to review things that we discussed that you will need, like toolbox you will need. So these are the things we discussed before. In general, when we have a reaction, we can plot it as, we see this, the simpler version of thermodynamics and kinetics before, but I'm just gonna show it again. So this is what we call a reaction coordinate diagram, right? You start from the y-axis being your energy, the x-axis being your reaction coordinate. Reaction coordinate basically say that's your reactant to product. When we are referring to the thermodynamics of the reaction, we're talking about the relative differences in energy between your reactant and product. So that's thermodynamics. So if the reaction releases heat, we say it is exothermic. If the reaction absorbs heat, we say it is endothermic. Right, so along the reaction profile, we also have transition state. And the relative energy between your reactant and your transition state, that describes the kinetics of the reaction, aka how fast the reaction takes place. For a more complicated reaction like this one, you could have multiple transition states along the reaction coordinate, which in this case, you can have a reaction intermediate that's being generated and falsely consumed to form the product. And whenever we have a two-step reaction, we're always talking about the highest point being our rate limiting transition state. All right, so these are some of the terminologies I might be using when we're talking about the reaction mechanism of each reaction. All right, and in our last lecture, we also discussed reactive intermediate. So what are the three classes of reactive intermediate we discussed? You either have a carbocation, a radical, or a carbanion. So that's the series we went over. You have the carbocation, you have radical, you have carbanion. So for carbocation, we say the tertiary is more stable than secondary, than primary. And what does it mean when we say tertiary? Tertiary carbocation is a carbon with 3 different R groups attached to it. Tertiary is a carbon with 2 R groups and then a hydrogen. A primary is a carbocation with 2 hydrogen and only 1 R group attached to it, right? Tertiary more stable than secondary, than primary. Likewise, for radical, we have tertiary more stable than secondary, than primary. Tertiary means you have, well, 3 things, 3 R group attached to it. Secondary is you have 2 different R group attached to it, and a hydrogen. Primary is carbon center radical with 2 hydrogen, 1 R group. Carbanion is a special case, because for carbanion, your primary carbanion is more stable than secondary, than tertiary. But the same applies, right? Primary, only 1 group. Secondary, 2 R groups. Tertiary, 3 R groups on it. And these are my intermediate. That's reactive intermediate. It will be formed and consumed right away. All right. And as a final note, reaction enthalpy. So these are the thermodynamics we discussed. So the reaction enthalpy is telling us that's the bond dissociation enthalpy, or the energy needed to homolytically cleave a bond. So the larger the bond dissociation enthalpy, the stronger the bond. And the typical reaction of the enthalpy can be calculated based on the bond dissociation enthalpies of your reactant and product. So these are all reviews. of like things we will be talking about. So in our next lecture, we'll start by looking at a general mechanism for all alkene involving reactions, and then we'll look at case by case on selectivity and reaction conditions of the alkene involving reactions. So I'll see you next Monday.